This last chapter in our text presents and describes one test statistic, the chi-square test, from a family of test statistics we call non-parametric tests. All of the test statistics you have learned so far are considered to be parametric tests because the measurement system we have used has been based on either an interval or ratio system. When you use a measurement system composed of values that are based on numbers that span a range of values, you are able to array those numbers into a distribution, like you first learned in Chapter 2. And the shape of the distribution is important. However, sometimes a researcher uses a nominal or ordinal measurement system to gather data from subjects. When that is the case, the researcher cannot use parametric tests and instead must use a non-parametric test. There's a family of non-parametric tests that are considered equivalent to the parametric tests you have learned about. In this chapter, you will learn about two versions of the chi-square test statistic. Parametric tests possess the advantages of being fairly robust, and because they use scale data, which allows one to measure variance, have more power efficiency, if their assumptions can be met. However, when departures from the assumptions of normality or homogeneity of variance are severe, when the data are nominal or ordinal, or when the research question addresses issues other than the value of specific parameters, a non-parametric method may be more appropriate. We will learn about two variations of the chi-square test statistic, the chi-square goodness of fit test and the chi-square test of independence. Shown on the slide is the chi-square formula. The notation for the chi-square test statistic is the italicized capital X squared, and mathematically, it is a pretty simple formula to compute. First, find the difference between the observed frequencies, the data, and the expected frequencies, which represent the hypothesized population proportions for each category. Second, square the difference. This ensures that all values are positive. Third, divide the squared difference by the expected frequencies. Fourth, sum the values from all the categories. The notation for the observed frequencies is an italicized lowercase f with an O subscript. The notation for the expected frequencies is an italicized lowercase f with an E subscript. We will be using this formula for both the chi-square goodness of fit test and the chi-square test of independence. The difference will be in how we calculate the expected frequencies.